Hello again, Advanced Kentucky AP Chemistry students. This is Lou Akampora, the Science Director, and let's get right into today's topic, which is intermolecular forces and properties of matter. I hope this will help you as you prepare for the Advanced Placement Chemistry test. A little bit of information and then we'll look at some practice problems, but most of you know, I think, that all of chemistry is really trying to explain how matter behaves in terms of the particles, and they are atoms or molecules or ions or electrons, and please do be sure to get the vocabulary correct. These are forces, these particles respond to forces that are electrical in nature. So we talk about Coulomb's law, and Coulomb's law says if we have two charged particles, call them Q1 and Q2, and those could be ions or electrons or a balloon that you rub your hair with or something. There's going to be a force between them and an energy because of that, and the energy is proportional to the product of those charges, Q1 times Q2, and inversely proportional to the distance between them. If it were the force, that would be d squared, but for energy it's just a single term of d. You'll never need to use this equation, but being able to interpret the physical properties of matter in terms of the charges and the distance between them will really help. And I know very good students who have a hard time understanding and explaining intermolecular forces because they try to memorize things rather than build a model and understand. And AP Chemistry is really about building these models and trying to interpret them, so to explain properties of matter. Well, what are we trying to explain here? And they are not the chemical properties about reactivity, but we're really looking at how the strength and types of these intermolecular forces might affect things like boiling points or melting points. You might guess that things that have a high melting point or a high boiling point would have stronger forces between those particles. Vapor pressures is related to that. Whether something evaporates easily, is quite volatile and has a high vapor pressure. The electrical conductivity of a substance, whether it's a solution or even a solid, and remember that to conduct an electric current, the substance has to have charged particles, but they also have to be able to flow. An electric current is a flow of charged particles, and those could be ions in solution. They could be electrons. And maybe the solubility, and if we have whether or not one substance will dissolve in another, or the relative solubilities of two different solutes into a solvent, which would depend on identifying the character and strength of intermolecular forces, not only in the two solutes, but also relating them to the intermolecular forces of the solvent. So that's really what we're looking for, how to explain these things in terms of the particles. Remember that intermolecular forces are different from covalent bonds. They are generally weaker than covalent bonds, although we'll see in one instance they are in fact covalent bonds. But we've got to, in your writing, as you explain this on the AP Chemistry exam, your explanations have got to make it clear what you are referring to. And also, the stronger the forces, the more energy it's going to take to overcome them. So when we talk about vaporization or melting, the magnitudes of those energy changes should be related to the strength of those forces. I hope you all have a page of notes that discusses some of this, and then I just want to quickly go over what I would say are the four common classes of substances and the properties that we might expect. And this is the way that matter might arrange itself. Again, this is nothing you should be memorizing, but things that you would be well served to understand. So I know the first class here on my little cheat sheet talks about ionic compounds, and as you would suppose, ionic compounds are made up of ions, positively and negatively charged particles. Then the classic example would be what you likely sprinkle on your French fries or into your soup, and that is sodium chloride. You know that if we write NaCl, that little white crystal is not composed of sodium atoms and chlorine atoms, but rather sodium ions, sodium atoms that have lost one electron and gained a positive charge, and chloride ions, which are chlorine atoms which have gained an electron. So a good model that you might keep in mind is positive ions, which I'll represent here in red. And in between them, the negatively charged chloride ions, which will be here in green. Of course, the ions themselves aren't colored, but this is a good representation. And positive ions are typically smaller than negative ions, so I've tried to show that here. And again, there would be layers coming out of the board atom, so it would be a three-dimensional crystal. What holds this together are the electrostatic attractions between the particles. Since we've got a charge of +1 and a -1, or if you watch the electrochemistry video, plus 1.6 times 10 to the negative 19th coulombs as our unit of charge, and negative that same number. But we've got these charges, and they're separated by some distance d, and for an ionic compound, that distance would be the distance between the ionic centers, which would be the sum of the two radii, called it R1 and R2. In order to, if we were to take this solid sodium chloride and vaporize it, we turn it into a gas of sodium ions and chloride ions. So now we would have these negative ions that are quite separate from each other, and from a molecular or atomic point of view, far enough apart that they no longer interact. It would take a lot of energy to do this, because these are full charges of 1 plus or minus 1 electron. The amount of energy it takes to do this, well, we usually talk about the energy released when the separated ions associate to form the compound, and that's called the lattice energy. We could write the lattice energy as the sum over all ion pairs of the formula that we had on the board earlier for Coulombic energy, K times Q1 times Q2 over D, where these are the charges of the ions, and if I have a mole of sodium chloride, which would have 1 mole of sodium ions and 1 mole of chloride ions, this is going to be a huge number of ion pairs, but if we could take the sum of all of these contributions, we would get a lattice energy. And for sodium chloride, it has a value of approximately negative 700 kilojoules per mole. That's a pretty big number. It takes 700 kilojoules to vaporize a mole of sodium chloride, which is why if you happen to spill a little crystal of sodium chloride, it doesn't evaporate. Ionic compounds won't do that. But more important than the absolute number is the trend in sodium chloride. And I want you to note, look at this formula and say, well, the lattice energy, which will always be negative, that's holding things together, they're more attractive forces than repulsive forces, will depend on the product of the charges. If I have charges that are plus or minus 2, I'd have a more negative lattice energy. And the distance between their centers. And the larger the distance between their centers, since that's the denominator here, the less negative the lattice energy. And we can explain many of the relative properties of ionic compounds in terms of this formula. So if I had a different compound with the same plus and minus 1 charges, and perhaps not sodium chloride, but potassium bromide, potassium bromide would still have ions with charges of +1 and -1, but the potassium ion has an extra shell, so it would have be slightly larger than the sodium ion. The bromide ion is larger than the chloride ion, and the distance between their centers would be correspondingly greater, and potassium bromide would be expected to have a less negative lattice energy, and therefore a lower melting point, weaker forces holding these ions together. And I'll let you consider what might be true for magnesium sulfide, MgS, but I want you to think about the charges on the ions and how far apart their centers might be. So you hope that in order to answer these questions, you need to be able to identify ionic compounds, and I think most of you will be able to do that pretty well. Given that model, what kind of properties would we expect? Well, we expect that if you ever have a high melting point because these lattice energies are very, very negative, that these compounds are very brittle. It's very difficult to push ion layers past each other. So then you think about the properties of salt as your typical ionic compound. The solubilities, well, they might dissolve, but they would dissolve only in very polar solvents. Classically, water is the most polar solvent because if we have a sodium ion and you know that water is polar, so the polar water molecules will be attracted to the positive ion with the negative end of the dipole attracted to the positive ion. And similarly, chloride ions will also be attracted to water molecules, but this time the water molecules will point with the hydrogen or positive end of the dipoles pointing in toward the negatively charged ions. And frequently, students are asked to produce or interpret pictures like this that represent the hydration of charged ions by these polar water molecules. And these should make sense and perhaps be familiar to you. Okay, so that's really the important model for ionic compounds, and there are many of them. The second class of compound is things we're all familiar with, and those are molecular covalent compounds, things that are made up of molecules in the very, very specific sense of a group of atoms bonded together with no overall net charge, so things like water or benzene or methane or ammonia, these are all molecules. And when we have molecular compounds, or even molecular elements, so even though oxygen and argon are not compounds, I'm going to group them into this class as being composed of molecules or even atoms, but having very, very weak intermolecular forces between them. And again, if we look at Coulomb's law, putting it up one more time, if Q1 or Q2 are zero, or both are zero, it's hard to see why there would be any energy of interaction between them. And that's true, but the caveat here, the flaw in that thinking, is that Coulomb's law really only applies to point particles, and molecules are distributed. So we could have attractions or repulsions between different parts of a molecule. And these intermolecular forces, the intermolecular forces in molecular compounds, really come in three different types. And it's not enough to memorize these types, but you should understand what generates the types, these different forces, and what their magnitudes depend on. So I'll start in the middle, and the second type of intermolecular forces we might call dipole forces. And these come about because some molecules, such as water is probably not a good example, but let's say hydrogen chloride or carbon monoxide. If we have a carbon monoxide molecule, the oxygen end is more electronegative than the carbon end. So there's a net dipole. This acts as if there's a slight negative charge on the oxygen end and a slight positive charge on the carbon end of the molecule, which, even though it's neutral as a whole, has a charge distribution. If I have two carbon monoxide molecules, well, the positive end of one molecule would be attracted to the negative end of the other, and the negative ends would be repelled and the positive ends would be repelled. And if I had three carbon monoxide molecules, they might arrange themselves like so. And if I had enough carbon monoxide molecules, I would get this structure where these molecules are held together, similar to magnetic forces, slightly different, but similar enough that we could use the analogy. And they would be attracted because parts of the molecules have small charges. Remember that the symbol delta with a plus or minus tells me it's a partial charge. So these are much, much, much weaker than ionic forces or lattice energies, which deal with complete charges. So dipole-dipole forces occur in molecules that have a permanent dipole or polar molecules. And they depend on the magnitude of the dipole moment, which is a fancy physics way of saying how polar the molecule is. So you'll see numbers for dipole moments. These are typically measured in units called debye's, but we don't need to worry too much about that. But the bigger the dipole moment, the stronger these dipole-dipole forces are going to be. These exist really only in molecules that have a permanent dipole. But things that are nonpolar, things like halogen molecules, fluorine or chlorine or bromine or iodine, or hydrocarbons like methane and ethane, propane, and so forth, these also have intermolecular forces between them, even though they're nonpolar. And these are called dispersion forces, or London dispersion forces, after the scientists who first explained them. So if you were to write LDF, or London dispersion forces, most of the AP readers would know what you're talking about, and they would all give you credit for it if it was appropriate. Where do these come about? Well, even if a molecule is nonpolar, in general, or on average, it might have an instantaneous dipole. And let me illustrate this with probably the simplest particle that we can, and that might be a helium atom. A helium atom has a nucleus with 2 protons in it and 1 or 2 neutrons, and an electron cloud with 2 electrons. On average, those electrons will be symmetrically distributed about the nucleus, but because of quantum mechanics and the weird properties of matter, it might happen that these 2 electrons might find themselves in the same area of the nucleus at a particular instant in time. A moment later, a femtosecond later, or even shorter, those electrons might be here and here. And remember, this is a spherical particle, so I can only draw on the board, but the electrons might be here and there. But there might be an instantaneous dipole that's going to fluctuate. So this dipole, represented here by an arrow, might be a small one there, and then shortly later there. Well, as this fluctuating instantaneous dipole pops into existence, on average it's going to cancel out, but a neighboring helium molecule, helium atom, not a helium molecule, might respond to this instantaneous dipole by inducing a dipole. So if the electrons are over here on the left-hand side as I'm drawing this, and the proton nucleus is here, this might pull electrons from the neighboring helium atom over this way and induce a dipole over here in the second atom, and this would have the net effect of causing an attractive force. So these dispersion forces are due to fluctuating / induced dipoles. The strength of these forces, these are not necessarily weaker than dipole-dipole forces. In fact, they could be quite strong. Something like iodine is a nonpolar molecule, and each iodine molecule, each I2 molecule, has 106 electrons in it, 53 from each atom. And iodine's a solid at room temperature. Pure iodine would be a solid. So you may be familiar with that. The point is that the strength of these dispersion forces varies with the number of electrons or the size of the electron cloud, or the fancy word for that is the polarizability. Polarizability. ability. How easy is it for these electrons to be pulled or pushed to one side or another to generate this induced dipole? So the polarizability is not the force. The force is called the dispersion force, but it is the factor that governs the strength of these dispersion forces. And dispersion forces are present in all forms of matter. Even ionic bonds have dispersion forces, or ionic crystals have dispersion forces, but in this case, they're swamped by these much stronger electrostatic forces. And finally, the third, and generally, all other things being equal, strongest intermolecular forces are those hydrogen bonds, very poorly named, because they are not covalent bonds. They are, in fact, intermolecular forces, and students who write about hydrogen bonds really need to be careful to make that clear. If we have a hydrogen atom at the positive end of a dipole, so if our hydrogen atom is bonded to another atom that is small and highly electronegative, and that's usually going to be oxygen, fluorine, or nitrogen. I'll make it a fluorine here. Well, this is not a hydrogen bond. That's your everyday covalent bond caused by sharing electron pairs. But if I have this hydrogen will have a partial positive charge, and the fluorine, because of its electronegativity, will have a partial negative charge. A neighboring hydrogen fluoride molecule would be pulled to arrange itself like that. This intermolecular force is what we refer to as a hydrogen bond. Now, it might look just like your typical dipole-dipole force bond. But because the hydrogen is special, the hydrogen atom, remember, only has that one shell, that one electron, so when it acquires a positive charge, there's really a bare proton here, and that means that this hydrogen bond is going to have some extra strength, which is really a quantum mechanical phenomenon, but these hydrogen bonds tend to be stronger than you would expect based on the dipole moment of the molecule. So hydrogen bonds are bonds that occur between the hydrogen of one molecule and the small electronegative atom of a different molecule, and that's the hydrogen bond. Remember, it is an intermolecular force. It's not a covalent bond, and it's much weaker than these covalent bonds. And covalent bonds, single covalent bonds, typically have bond dissociation energies of several hundred, 250 to 400 kilojoules per mole. Hydrogen bonds, even though they are fairly strong by intermolecular standards, will have bond dissociation energies or intermolecular dissociation energies of about 20 kilojoules per mole. So because these intermolecular forces, no matter what flavor they are fairly weak, these substances tend to be low boiling points or low melting points. If it's a liquid or a gas at STP, it's probably a molecular substance. They tend to be waxy. You can push the solids particles past each other. They do not have free charged particles, so they don't conduct an electric current. They're electrical insulators, either as solids or liquids. And they may dissolve, but if they dissolve, they dissolve in a solvent of like polarity. And the aphorism is like dissolves like, but don't write that on the AP exam without explaining that it's the polarity of the solvent and solute that will really make a difference, what we're talking about. Those ionic compounds and molecular compounds are the two, I'd say, most important or most common classes of substances. We should also mention that there are two other types we'll spend very quickly talking about, and one is the network covalent substance. And that happens as it might suppose. We've got covalent bonds, but there's a network that extends throughout the crystal. So if we talked about carbon dioxide, most of you know carbon dioxide is a gas and is composed of discrete carbon dioxide molecules, which are nonpolar and have therefore only fairly weak dispersion forces between them. And carbon dioxide is a gas at room temperature. If we consider silicon dioxide, and silicon is right underneath carbon on the periodic table, we might expect to have something that looks like this on a molecular level, a slightly higher boiling point because silicon would have a few more electrons than carbon, but certainly possibly a gas or a liquid at room temperature. What we find, though, is that silicon dioxide is a very, very high melting point, 1700 or so degrees Celsius, certainly much higher than you would expect from weak intermolecular forces. And you've all seen silicon dioxide, I'm sure. If you've been to a beach, the stuff you're walking on, the sand, is fairly impure silicon dioxide. And that's because silicon doesn't form double bonds with oxygen very readily, and instead what you get is a picture which is not very realistic because this is constrained to 2 dimensions here, but you get a model where covalent bonds extend throughout the crystal. So you get this structure here where a grain of sand is really one huge molecule with 10 to the 22nd silicon atoms and twice that number of oxygen atoms. And you can see the empirical formula, if I were to keep extending this, would be SiO2. But the covalent bonds really are the intermolecular forces. And because of that, these are very directional. Sand is very brittle. It has a very, very high melting point. It doesn't dissolve in anything, certainly not in water, or the beaches wouldn't be where they are. And doesn't conduct an electric current. So don't try to memorize the list of things that form network covalent compounds, but recognize what their properties might be based on this model of bonding. And then finally, one of the more interesting and technologically useful classes of matter are metals. And metals, most of the elements are metals, as are alloys. And the most important property of metals is that they can conduct an electric current even as a solid, which means there have got to be charge carriers that can flow, even though the metal itself, a wire, isn't going anywhere. Metals typically are made of atoms that have low electronegativities, and we could think of, for example, a piece of metallic sodium, as being composed of sodium cores, the nuclei plus the inner electrons, where the valence electrons are free to move, are shared or delocalized among all of the nuclei, and therefore these negatively charged electrons can flow when an electric field is applied. So, in sodium chloride, I would have immobile chloride ions in between the sodium ions, but a model for metals is that I've got these positively charged metallic cores immersed in a C, the delocalized electron C model of mobile electrons. These bonds can be quite strong, and metals can have very, very high melting points, like tungsten, or very, very low melting points. Mercury, you probably know, is a liquid at room temperature. But metals tend to be malleable. Because these electrons can flow, we can push these layers of cores past each other. And again, the important property is that even as solids, metals will conduct an electric current. So that's a quick overview, maybe not so quick. But this would be a good time to pause the video, and if you have the questions, maybe think about answering them yourselves, and I'll kind of give you a moment. Well, pause the video, and then we'll look at some of the questions that might be asked on the AP exam. So we've got a couple of multiple choice questions here. And the first one asks for which of the following processes are covalent bonds broken. I'll not put these on the board, but I'll just read them off. We got I2 solid going to I2 gas, chlorine solid going to 2Cl gas, NaCl solid going to Na plus Cl minus in water, that's a dissolving of salt, and copper solid going to copper liquid, that's just melting copper. I hope you all picked B for that. In option A, you're just taking solid iodine molecules and separating the molecules, but you're really only overcoming the intermolecular forces between iodine molecules, and those would be dispersion forces. In option C, solid sodium chloride is dissolving, which means you're overcoming those ionic or lattice energies and substituting it for the energy of hydration between those ions and the water molecules, since that aqueous, in parentheses, tells you you're dissolving this into water. And solid copper melting to copper liquid would really be overcoming metallic bonds. So I hope that was one that you all got. Question 2 talks about the melting point of magnesium oxide is higher than the melting point of sodium fluoride, and you're asked which factor does not contribute to this. So if we had sodium fluoride, I would have a sodium ion and a fluoride ion, and here's my NaF. And notice that both of these ions would have the same electron configuration of neon. They would each have 10 electrons. Sodium nuclei have 11 protons, fluorine nuclei have 9, so this would be a little bit bigger, but they'd be separated by the sum of those radii. If I have magnesium oxide, well, magnesium ions and oxide ions also each have 10 electrons. Magnesium ions have 12 protons, so we get a slightly smaller ion with a charge of +2, slightly smaller than the sodium ion. And then oxide ion that is slightly larger than the fluoride ion with a charge of -2. And I might expect then that the distance between these ion centers would roughly be the same. But here the charges on these ions are +2 and -2 instead of +1 and -1, so I would expect a much more negative lattice energy. The fact that the oxide ion is larger than the fluoride ion does not help here, but all A's, B, and C will contribute to making this a more negative value. So the answer to multiple choice question 2 would be choice D. The third question asks you to arrange the intermolecular forces from hydrogen fluoride, hydrogen chloride, and oxygen from weakest to strongest. So we've got O2, HCl, and HF. And it's going to be in this order. You should recognize that hydrogen fluoride will form hydrogen bonds. Neither of these will, so that will be the strongest. And between hydrogen chloride and oxygen, well, hydrogen chloride will be polar and it will have more electrons total. Hydrogen chloride would have 1 + 17 or 18 electrons, and not just valence electrons. All of these electrons will contribute to the dispersion forces. Oxygen molecules will have 2 × 8 or 16 electrons. So we would expect the lowest boiling point to the highest boiling point to be in that order. Okay, moving on, the fourth multiple choice question really addresses a common vocabulary error, and that asks for the strongest intermolecular forces present in liquid hydrogen. So if you were to cool hydrogen down enough, it would liquefy, and you would see these hydrogen molecules that are now attracted to each other. There are no hydrogen bonds in liquid hydrogen. Remember, hydrogen bonds occur only when the hydrogen atom is bonded to a small electronegative atom. In fact, these are covalent bonds. The only forces present in liquid hydrogen, since hydrogen and molecules are nonpolar, would be dispersion forces. Okay, nonpolar substances with low molecular weights have, well, nonpolar and low molecular weights would mean only dispersion forces, and they would be weak, so you'd have low boiling points. And again, I hope you're all thinking of not memorizing these properties, but the models that we had on that first page of notes. If you have a brittle solid with a very high melting point that will only conduct an electric current in the molten state, well, very high melting point tells you anything except molecular solid. Brittle would eliminate metals, because metals we think of as malleable. So our choices are network covalent or ionic, but network covalent substances, if you were able to melt glass or melt sand, they would not form charged particles. So the multiple choice 6, we've eliminated everything except the ionic substances. Multiple choice question 7 talks about solubility, and you're asked which is expected to be most soluble in carbon tetrachloride, a non-polar solvent, and you would look for something that is a molecular substance that is non-polar. Ammonia is molecular but polar and forms hydrogen bonds. Calcium chloride, which is mislabeled D, but it's the wrong answer, is ionic, and iron is metallic, so iodine would be the choice there. Going on, multiple choice question 8, carbon tetrachloride, which is a liquid at room temperature, but methane is a gas. Both of these compounds are nonpolar. If anyone wrote about A, well, A or B are wrong, because we're not dealing with the strength of the bonds, we're dealing with intermolecular forces. Carbon tetrachloride, if it were a network covalent solid, well, it couldn't be because chlorine will only form one bond, but that would have a much higher melting point. So the best answer for multiple choice question 8, in fact the only correct answer, would be D. And then questions 8 through 11 ask you to identify those substances in terms of the models, not the names, but the models of their bonding. Cesium chloride is an ionic compound, so we would guess that would be, or not guess, we would write that that's a lattice of positive and negative ions held together by electrostatic forces. Gold, you all know, is a metal, I hope, and that would be the choice B, a closely packed lattice with delocalized electrons. Carbon dioxide and methane are both molecular substances. Carbon dioxide, though, because it has double bonds, would have sigma and pi bonds, and methane would only have sigma bonds. So carbon dioxide would be D, and methane would be C. Moving on, question asked about rubidium and bromine to form rubidium bromide, which rubidium is a metal and reacts quite vigorously with liquid bromine to form the ionic compound rubidium bromide. We could talk a lot about this, but this question only asks which of these would be good electrical conductors, which means we've got to have charged particles that can move. Solid rubidium is a metal. You don't usually think about it. You've probably never seen solid rubidium, but it is a metal. It's on that left-hand side of the periodic table, so it is a good electrical conductor. Pure bromine is a liquid, molecular compound, not a very good conductor. Rubidium bromide, Br, palindromic, if you ignore the capitalization. As a solid, well, it's got charged particles, but these charged particles are held rigidly in place, so it's not going to be a very good conductor. If, however, you heat up rubidium bromide sufficiently, and because we've got charges of plus and minus 1 and fairly large ions, its melting point, I would guess, would be close to 600 degrees Celsius. High, but hot enough that you could melt it with a Bunsen burner. These particles would no longer be held in place, so liquid rubidium bromide would be a pretty good conductor. And if we have a solution, if we take our rubidium bromide solid and dissolve it into water, this will really separate, dissociate into ions which can flow, and solutions of ionic compounds are generally excellent conductors. So there are 3 of those that would be pretty good conductors because there are charges that can flow. Moving on, we've got 4 quick questions here. Things you're asked to explain. You're given in question, the first part of the next question, the structures of pyridine and benzene. And you're told that pyridine is soluble in water, but benzene is not soluble in water. And then asked to account for the difference in solubility using appropriate principles of chemical bonding and intermolecular forces. So remember, when you're talking about solubility differences, it's not only pyridine and benzene, the 2 solutes, but also the solvent, which in this case is water, and you've got to identify and talk about the intermolecular forces. In this case, because pyridine is not only polar, that nitrogen atom in the ring has a partial negative charge, but also is able to form hydrogen bonds through that unshared electron pair. Pyridine is polar and can form hydrogen bonds with water, whereas benzene is nonpolar and cannot, even though it's got 6 hydrogen atoms in the ring. Neither of those are directly bonded to a oxygen, fluorine, or nitrogen. So benzene is a nonpolar molecule that cannot form hydrogen bonds with water. And that would be enough to, you identified a difference and talked about how it interacts with water. That would be enough for full credit on that. The second part of that question tells you that the normal boiling point of chlorine is higher than the normal boiling point of HCl, and gives you the numbers there. And it's very tempting to look at chlorine and say that's a nonpolar molecule. Then HCl is a polar molecule, and you might start to write that polar molecules have dipole forces and therefore would be higher boiling. But if you look at the numbers, don't be seduced by a good explanation that doesn't fit the facts. In fact, chlorine has higher boiling point, even though it only has dispersion forces, but chlorine has, in a molecule, 34 electrons and stronger dispersion forces than the 18 electrons in a hydrogen chloride molecule. And these extra electrons, the additional dispersion forces, more than makes up for the fairly weak dipole forces. Part C here talks about the melting point of sodium fluoride compared to the melting point of potassium chloride. And again, those substances are both composed of ions with charges plus and minus 1, but the sodium fluoride ions are smaller, and therefore the distance between their centers is less, and therefore there's a more negative lattice energy compared to potassium chloride. There's a tendency for students, whenever they see something with fluorine, to talk about the hugely electronegative atom of the fact that fluorine is a huge electronegativity. That will really only be important if you're talking about the polarity of covalent bonds, and that's not the case here. And then the last part of here tells you that sulfur dioxide melts at negative 172 degrees Celsius, but silicon dioxide melts at 1610. You could look at that and say, well, are these dispersion forces differences? Are these differences in dipole forces? But look at the numbers and again, interpret the data. It's not a small difference in melting points, but rather a very, very large difference in melting points. 1610 degrees Celsius is hotter than you can easily get in the lab. And that tells you that silicon dioxide is probably not going to be a molecular compound. In fact, it's a network covalent substance. So identifying SO2, sulfur dioxide, as a molecular covalent substance with weak intermolecular forces, which in this case are dispersion forces and dipole forces, but silicon dioxide would be a network covalent substance whose intermolecular forces are in fact stronger covalent bonds. And then finally, you're given this table, and this is from a recently released AP exam, a very nice question. I wish I'd written it. You're given data for the boiling points, dipole moments, and polarizabilities of the 3 hydrogen halides, hydrogen chloride, bromide, and iodide. First, you're asked what type of intermolecular forces is able to account for the trend in boiling points, and you would look at that data and notice that as the molecules get larger, the boiling points go up, the dipole moments in Debye decreases because there's a smaller electronegativity difference between the atoms. but the polarizability increases. So it looks like the boiling point trends with polarizability. Remember, polarizability is not a force. Polarizability governs the dispersion forces. So a good answer here would be to say that because the boiling points correlate with polarizability, it is the dispersion forces that account for the trend in boiling points. Part B asks the students to explain why the observed boiling point of hydrogen fluoride is much, much larger and than expected based on the trend. And the student would be expected, and I think we've already talked about this, identify the fact that hydrogen fluoride molecules can in fact form hydrogen bonds, which the others cannot. So if you have an HF, because its hydrogen atom is directly bonded to a fluorine, it can form these hydrogen bonds, which are stronger than the dipole forces you would expect from the other hydrogen halides. And then finally, you're given this representation of 5 hydrogen bromide molecules in the liquid phase in a box, and asked what happens when they vaporize at 207 kelvins. And the important thing here is to understand that HBr liquid going to HBr gas does not break these molecules apart. So students who did this would be incorrect. You're just asked to separate the molecules and arrange them somewhat randomly and throughout the space. So that would be a good picture for that. Okay, let's pause here for a sec.